Dear RDA community, my name is Matthias König and I lead the Systems Medicine of the Liver Research Group at the Humboldt-Universität of Berlin. Today, I will present data and workflows to ensure the reproducibility of digital twins in pharmacokinetics. Let me start by introducing the concept of the digital twin. The digital twin is a virtual representation of a real patient, enabling the computer-based exploration of individual medical questions. It is built on mechanistic computational models which are personalized using patient-specific data, such as laboratory values, medical imaging, genomic data, or sensor information. The goal is to generate more precise predictions of disease progression or treatment effects, thereby providing better support for medical decision making. A central application area of my research is the digital twin in pharmacokinetics. That is the question, how are drugs absorbed, distributed, metabolized, and excreted in the human body? A key question in this context is, why do drugs work better in some people, while in others they are less effective or cause side effects? The goal is to use simulation-based predictions to contribute to a more personalized and safer medication strategy. To make the concept of pharmacokinetics more tangible, I'd like to show you a simple but very illustrative example: caffeine. We're looking at a healthy young woman who drinks a cup of coffee. This corresponds to approximately 100 milligrams of caffeine. After ingestion, the caffeine concentration in the blood rises and reaches its peak concentration after about 1 hour. After that, the concentration gradually decreases. In the liver, caffeine is metabolized into paraxanthine, an important step in the individual degradation process. If we repeat the same experiment with different individuals, we observe clear differences, both in the maximum concentration and the time to reach the peak. And this is exactly where my research comes in. Where do these differences come from? Which physiological, genetic, or disease-related factors influence pharmacokinetics? A key building block in the development of reproducible digital twins is the integration of heterogeneous data. To supply our pharmacokinetic models with high-quality data, we developed PKDB, an open structured database for pharmacokinetic time courses and parameters. PKDB contains data on a wide range of drugs and test substances, including a variety of clinically important compounds, liver function tests like ICG and caffeine, substances for metabolic phenotyping such as dextromethorphan or chlorzoxazone. The data are standardized and FAIR compliant, enabling comparative analysis and development of computational models. Thanks to the standardized and structured storage in PKDB, it is possible to perform cross-study analysis. For the substance caffeine, for example, we were able to create a comprehensive meta-analysis of its pharmacokinetics based on data from numerous studies with different doses, populations, and study designs. Such analyses are crucial for model validation, quantifying inter-individual variability, and developing realistic digital twins. Today, I want to demonstrate at the example of glimepiride, first, how patient-specific factors can be integrated with these digital twins, and second, how we can ensure the reproducibility of the results. We have a look at glimepiride, a medication used to treat type 2 diabetes, which affects over 500 million people worldwide. Glimepiride stimulates insulin release from the pancreatic beta cells, leading to increased glucose uptake in insulin-sensitive tissues and a reduction in blood glucose levels. We developed a detailed physiological-based pharmacokinetics models for glimepiride. At the whole body level, the model describes the systemic circulation of glimepiride and its two main metabolites, M1 and M2. In the intestine, we simulate absorption of glimepiride and fecal excretion of its metabolites. In the liver, glimepiride is metabolized via CYP2C9, first to M1 and then to M2. And finally, in the kidney, we model the renal excretion of M1 and M2. We applied this digital twin of glimepiride to study key factors affecting pharmacokinetics: the dose dependency, renal impairment, liver cirrhosis, the body weight dependency, effect of genetic variants, and simulated virtual patient populations. For instance, we use the model to assess the impact of CYP2C9 genetic variants, such as the STAR2 and STAR3 alleles, which reduce the enzyme activity. Reduced CYP2C9 function leads to higher plasma levels of glimepiride and lower levels of its metabolites M1 and M2. This demonstrates how the model can support pharmacogenomic informed dosing. So, how can we ensure reproducibility? A crucial factor for the reproducibility and interoperability of digital twins is standardization of the models, the data, as well as the processes, formats, and interfaces. Only through standardized structures can models be made more transparent, shareable, and reusable, whether in research, clinical practice, or within the scope of collaborations. As part of the combined initiative, we actively contribute to the development of such open standards. These include, for example, SBML for the structured representation of computational models, SED-ML for the specification of simulations, SBGN for standardized visualizations, PEtab for conducting and documenting parameter estimation, and OMEX metadata to document all models and data. These standards form the foundation for reproducible research, modular modeling, and cross-software interoperability. Around the core combined standards, we build workflows for reproducibility, called EXSIMO, Executable Simulation Model. The idea? Combine model, data, and code with the execution environment so analysis can be run automatically. Core elements are models and data and code for the computational analysis, automated tests to verify correctness, and an automation layer for continuous execution and validation. Within the executable simulation model, we integrate version control, annotations, unit handling, CI/CD, and reporting of results. We demonstrated the workflow in a replication study of the glimepiride digital twin, showing full transparency and reproducibility from data to results. In addition, we demonstrated reproducibility through an independent review by the Physiome journal, which confirmed that the entire analysis could be rerun successfully. A second independent review is currently in progress with the BioModels team, providing cross-platform verification of the results. If you like to explore and interact with the model, visit glimepiride.de, offering an interactive web application of the digital twin, or run the analysis yourself via the GitHub repository. I want to thank and acknowledge my funding and thank you for your attention.